But the main thing is down differential cross section. We'll see that in different limits of energies, when we go to hard spheres, we'll see very different, because these numbers are not constant, but they change.
So it's really interesting because this actually represents the literal cross section. If you were to look at the sphere classically, with one eye, you just see the largest circle there, which has an area of pi r squared. Also, this picture here is essentially directly from Griffiths. Just going to say that because I don't want to plagiarize or anything. But the truth is, even if, I could have redrawn it or whatever, but it would have looked exactly the same. It's the same good time. So the quantum treatment is a lot cooler, because now we're going to replace these BBs that we're firing in with just a wave coming in, a psi, a complex exponential. And I think you guys have seen this already. A lot of you have already talked about this. We'll just go over it really quickly. This is the incoming wave here. There's some normalization constant. And then the e to the ikr is just representing a spherical wave going outward. And the over r is going to make it so that we can sort of conserve probability, because as we go out, we want psi star psi to be the same no matter what sphere we're looking at. And then we want to throw on an angle dependence, because we don't really know what our angle dependence is going to be. It might be preferentially backward or preferentially forward. We're going to look at that. Okay, next slide.
Okay, so we've gone through this before already. Take the Schrodinger equation, separable. You have this differential equation, like the radial equation. We've seen all this business before. We go through, we get spherical Bessel functions, and then as Robert talked about, well, we can take linear combinations of these. Dan likes to call it like a cake mix, and throw them together, and we get the Hankel functions. And so, what we're going to end up with is the Hankel functions. And we want the Hankel functions and not the spherical harmonics, because they're in this nice form of e to the I stuff. And the sines and cosines are valid solutions. It's just they're not sexy, because we're not sending in sine waves, we're sending in these complex exponentials. Yeah. So that's the whole point for doing this.
Yeah, a cool way to think about it is that Hankel functions are to exponentials, kind of like the spherical Bessel functions are to sines and cosines. There's a analogous Euler's formula that deals with that. Instead of cosine plus I sine is e to the I theta, you have just something that looks exactly the same, except you just stick in your Hankel functions and spherical Bessel functions instead of the sines and cosines and the exponentials.
In the large R limit.
In the large R limit.
That's important.
Yeah. Okay, so let's talk about boundary conditions really quick. So in order to do this, we need to talk about what it looks like on the surface of the sphere. So maybe I'll use a little bit of board space here. Here's our sphere. We've got these waves coming in like this. And then we're going to hit this. But we need to make sure, because just like when you're dealing with a infinite square well, you know that whenever the potential is infinite, you can't find the particle there. So we require that psi vanishes at the boundary here. Okay? So maybe I'll write down a little bit of math that we don't actually have there. The formula that someone else derived, that L starts at 0 to infinity, the L, I believe, 2L plus 1, what this guy, what is it? Sine. No, it's
But you call it just A sub L for now if you want.
There's an A sub
You
L
can
in there.
express it in terms of
I thought there was something else. The Legendre polynomial is over here.
Mm-hmm. You could call it e to the I delta L times sine delta L over K.
I'm talking about the exact solution, even close to the sphere. I'm not talking about the large R limit.
I think it's just A sub L.
It's maybe it is A sub L.
If you want to do it in terms of phase shifts, like Robert did, just call it e to the I delta L over K.
No, that's not what. Okay, so I don't remember what's in here. It's a formula from the book. But what you can do is you can say, if I take this formula and I plug in r is equal to the radius of the sphere, then I'll take everywhere where I see an r here, I'll plug in capital R, and then I'll make sure that's equal to 0.
Okay.
And
I think I know what it is. You're matching boundary conditions.
Yes.
So you're writing e to the ikz in terms of these L's, the way
Yes.
Robert did.
Yes.
And that's what goes into this parentheses. That's
yeah.
the
I mean,
exact solution.
it's some math. I think it's it's J sub L of KR plus like I times the
N sub L probably.
times like N sub L. Yeah, something
the,
like
the
this.
Bessel function, the second kind. Yeah.
Yeah, okay, so whatever, it doesn't matter. But the point is, because of the orthogonality of these Legendre polynomials, and then you also plug in capital R here, like that. And then you see that in order for this to be 0, this has to be 0 if you want the Legendre polynomials to sum up because of the orthogonality. So this term here is never going to be 0, and neither is this one. So you're just going to have like J sub L of KR plus I N sub L of KR equals 0. You know what? There's an A sub L here somewhere. I think there's like an A sub L hanging out here. And all you have to do at this point is solve for A sub L, because that's what we're looking for ultimately. We're looking for the partial wave amplitude. So you go ahead and solve for A sub L and you get a formula. And now we can work off everything that all of you guys have built from. That A sub L, we have a formula for that. That's going to tell us about our scattering cross-section, and we're going to get some information from that. Okay, let's talk about that. So when you put all that in, when you go to the high energy limit, so you're sending in particles with really high energy, sending these waves with high energy, you get half of the surface area of the sphere. So it's almost like it's only, when these particles are going in, they're sort of going so fast that they're kind of missing the back part, and they're only sort of feeling the front half of the sphere that they're hitting. Conversely, if we look at the low energy limit, we get 4 pi r squared, which is the whole surface area of the sphere. So it's like they have time to sort of go all around and hit everything, which is really interesting.
What does that match up with in classical wave theory?
There's a long wavelength.
Yeah. So low energy means high wavelength, right? And high energy means low wavelength.
Right.
And what do we see when low wavelength versus high wavelength waves encounter a boundary, even in classical waves? Like, don't even know about scattering. Let's just say you see interference.
Low energy like goes around the.
Yeah. More importantly, what's the general term for that? Diffraction, right? Yeah. When waves bend around boundaries. So, for instance, if you have very loud sound waves coming out of a speaker, if I put a bowling ball right in front of the speaker, the bass waves I'll still be able to hear, but the treble waves will get more effectively blocked. And that's very similar to what's going on here. The bass waves kind of feel their way around the sphere and then continue on, whereas the treble waves tend to kind of come in, hit the front end of the sphere, and bounce off to the sides, but not caress their way around the sphere.
Yeah.
And that's essentially what's going on.
It's interesting you mentioned it, because coming up with, we have some graphs that will lighten that a little bit.
Okay, so this is going to go quick, but we've got a 3D version of this also. So what we're showing you here is a graph of the differential cross-section as it depends on theta, as it varies. Maybe I'll show that again. As it varies with k. How do I run that again?
I just go back forward.
Okay.
Very
So it
high
starts
tempo.
off like a circle. Well, it starts off like a circle, and then you see these interference paths.
Yeah, so you don't see it, but at the very first frame, when you'd have k getting very small, it actually looks just like a circle, which matches up with what we were talking about just a few moments ago, that the cross-section for low scattering is 4 pi r squared. It's like spread out evenly, just like a sphere would be. Now, if you look at this, you see these like lobes going on back here. And, I won't talk about why those are yet, but I think as we get farther in the slide, we'll start seeing what those really represent. Yeah, let's go to the next
So
one.
we'll show you the dress.
So
What?
here's
It's like a girl in a dress.
A girl in a dress? It's like a
Sideways, yeah.
Yeah, it's so
Oh yeah. Okay, so next one. Here's a
Here's the
3D
3D
version.
one.
So it's like you start seeing as we go up, as you were saying with this diffraction, you start seeing more and more of this.
Wait, don't go.
Oh, sorry, not the next one. How do I play it again? Can I just click it?
Do the high tech back and
Okay. Now, so low energy. It like you feel out half of it, and then you start to see one of these lobes.
Yeah, and it
And
kind of
then-
makes sense. It's
well-
like evenly distributed here, just like classically.
So, this
but
is
the
not
stuff
the
that's
whole-
actually getting around is doing weird quantum.
But remember,
stuff
this is
back
not the
here.
whole story. We're showing you. This started out as a circle, as a full sphere,
That's
and
true.
then now we're starting to show you how it evolves as we crank up the energy. So we start to see
Sorry,
one of these
I didn't
lobes,
say that. Yeah,
and we
this
keep going up and up.
animation is showing you K increasing over time. So the first frames are low K, and then we crank up K, and we see how we haven't told you a lot. I'm sorry. This graph here is a graph. We'll go back to the previous one.
Yeah, it's the angular distribution,
Yes.
and you're allowing K
So,
to change.
so the way
as
you
time goes on.
read this is you say, I want to know the differential cross section at theta is pi, right? So you look at the radius at that point, and that would tell you the differential cross section there. If you wanted to know the differential cross section at this angle here, you just read it off. So you can kind of imagine that like the farther it is from the origin, you're expecting like a lot of particles to go off in that direction. So I'm sorry. I
All right,
didn't
one more
really
time with the cool one. So yeah, the lobes are where it's like preferred. So like if you were to put your detector out here, like, that's the preferred thing where you'd see the more particles.
Yeah.
And this is what Dan was talking about earlier, how we can solve for these.
That's what I wanted to get. So if you would take this equation and solve for A sub L, I think you can see that you just subtract this on both sides, and you have a negative J sub L. There might be a negative sign here, but whatever. Here's that. And then we're dividing by all this stuff. There's also a K here that I forgot.
Yeah.
So the negative sign comes from a minus sign going down.
Yeah. So all the graph,
Numerator, denominator.
That's what it is.
all the
That's
graph
what
was that we just kept cranking up K, and then we took this A sub L, plugged it in, took the norm squared, and like that was. Go ahead.
Yeah.
So this equation is like an infinite sum. So does that mean like we have like full accuracy? Like we can use it in more than just like the radiation limit? Like can we use it closer?
Okay, so that's a good question. So this formula here is the F. And F squared, or a norm F squared, is going to give us the differential cross section, which is this graph here. That's telling us about what's going on far away from the sphere. But it's also interesting to talk about what's going on close, because differential cross section means you're kind of taking a limit. The particles are getting scattered. We're looking far enough away that they look like they're going out linearly, and we can talk about what it means for them to be diffracted at an angle. But luckily, the next slide we have actually does talk about what's going on close to the sphere. And it shows you how the waves are hitting the sphere and propagating off of it. So this is a graph of the real part of psi, because I can't very well show you a complex valued function. You know, it's kind of hard. So we'll just look at the real part. And you see these waves coming in from the left.
This is what Doug was talking about, this business, about like the probability be conserved. You see that like if it's really dark, that means it's like the density's higher. So you see that we have like this sort of light area here where there's less like probability to be. And that even cooler, I think, is that we sort of like see these little like I don't know, like streamlines or something of like these constant like strips or whatever they are.
Those are like your lobes, right?
Yeah, like these are like the
those are gonna be the
lobes.
lobes.
These are the lobes of where you're likely to find the particles. Go ahead.
So how is this different from a hard sphere moving through some sort of turbulent fluid?
I mean, I guess you could apply the math.
Like the
Well,
Navier-Stokes equation?
this is a good point. So remember, we drew an analogy yesterday between the flow of probabilities when Alex and Evan were giving their talk about the probability current. We drew, I think it was when they were, anyway, it doesn't matter. We drew an analogy between probability density in a fluid to like density, and flow of a fluid to being like the probability current, right? So what is different then? In both cases we got differential equations describing what's going on. What is different is the underlying dynamics. Okay, so there are fluid flow equations, the Navier-Stokes equation, and a couple other ones that describe the evolution of a fluid system like that. And then this one's different because we're having the Schrodinger equation describe its evolution over time.
Yeah.
So in terms of the pictures of the fields and the actual flows, you can make it a very strong analogy. Yes, the pictures look very similar. It's just different differential equations underlying, controlling the actual flow of these things. And specifically for quantum mechanics, what really makes it really different is that psi squared is the probability, but psi is the thing that interferes with itself. So it's kind of like saying if I have two electromagnetic waves coming in and hitting the same point, at one level you might say, oh, this one's bright and this one's bright, so when they hit it should be double bright. But that's not really what happens. You get interference fringes, right? You get points that are bright, points that are dark, different things going on.
Yeah.
So,
Yeah. So two things I'd like to say about that. The first thing is maybe the Navier-Stokes equations aren't so applicable, but what is really applicable is just the wave equation, like what Doug was talking about. If you have a bowling ball and you're, have a speaker and you're shooting these sinusoidal waves at it, that's going to be it's going to be relevant to the wave equation. And if you think about it, the Schrodinger equation is in some sense a wave equation, or it's very similar to a wave equation, especially when v is 0, because we're only talking about the regions where v is 0. So we don't have the extra plus v psi term. So all we're left with is just, the time derivative and the spatial divergence. I'm sorry, Laplacian. Yeah, Laplacian. So it does look very similar to a wave equation. So it's not surprising that we should expect to have these sort of patterns. And the other thing is that this is just the real part of psi. I've also tried graphing like psi star psi, and what's interesting about that is since the incoming wave is a complex exponential, it always has the same norm square.
Because you wouldn't see this red and blue on the left, right? So
instead, it kind of draws out some of the more interesting behavior because it's sort of showing you what kind of scattering is going on, because it sort of mutes out the incoming wave and you can see how stuff is reflecting off. And what happens there is instead of getting these waves coming in like this, you actually see what Alex was talking about. You see these like a wake, sort of. You see these curved lines showing you where the lobes would be. And they go on like this. I don't have a graph of that, but I thought this one was cooler.
Real quick, if those wakes out in front, if you were to take an object in classical, fluid dynamics and move it faster than those waves propagating, you would break either the sound barrier or something like that. Is there a quantum analog to that?
Okay, so what I'd say about that is the distance between these waves is going to be related to what k is coming in, or what the energy is that's coming in. So I feel like in order to do that, you'd sort of have to make the energy be so high that your incoming, the wavelength of your incoming wave would have to sort of go to 0. I don't think that's really physical because you can't really get that high energy.
Makes sense.
I think you could get them arbitrarily close. I don't think you could ever get it to pass itself, is what I'm saying.
My first thought would be, what is the quote-unquote sound speed of empty space?
The speed of light.
Yeah. My first guess would be you'd have to get to a point of relativity. You would have to get involved.
But at this point, the sphere isn't moving. You shouldn't think of the sphere as moving through the space. It's just sitting there, and the particles are coming in. So. One
last point about this graph, as long as you got it up here. Can you guys show me where the phase shifts are coming into play? You can actually see them.
Well, this is the destructive interference we're talking about here, and then the blue and the red are the different positive and negative.
It's interesting, but how far apart are these coming in?
Yeah, so see on the left, they're straight lines.
They're enhanced with here.
Yep.
But I don't know.
Well, it's not so much the width between them; it's the phase that's shifting. Right. So on the left side, you've got vertical lines dividing the red and blue, And on the right side, you see how it kind of curves in after the.
Yeah, that's a good point.
So that's the
yeah,
phase.
I was trying to compare it with my hand, but the truth is the ones up here don't change very much. So you can just that's true. You can see it curving in. You can see it at a delay. Yeah.
Okay. So that's that.
So
cool.
So that's our presentation.
Very very cool. Any questions for these guys?
Just a quick question. On the last graph, it looked like in 100B we did like conformal mapping for like fluid dynamics. Did they ever use that to solve for psi?
We didn't need to do that.
We didn't use that because we just used the summation formula and took enough terms that it started to converge.
Maybe you could do it then.
There's a one-to-one mapping from your potential.
Mechanics.
Yeah.
I'm sure. It possibly could. Go ahead. Yeah.
I think, there's. It depends on what symmetry the operator's perspective. You can't always use conformal.
That's true. You can't always.
Some operators, some weird situation maybe, but
Well,
like
the heat.
quantum fluid there a lot, but not in quantum. Straight up quantum.
The heat equation is just del squared, right?
Just let it cool down for a while.
So that would be, we can use the heat equation, we can use conformal mapping for heat equation, so we must be able to use it for at least the momentum part.
There's one difference between the heat equation and the Schrodinger equation.
Oh yeah, one's homogeneous, or one's equals 0.
There's also an imaginary there's a variable that doesn't map. There is actually a way to map between them, but it's the imaginary time.
Okay, so we got one more presentation. Manuel and Renato.